So for our project, we found a video online that had gone viral about 3.5 months ago that was posted by Roman Ursuhak, who demonstrated how to cut a glass jar using water, oil, and a heated piece of metal. We found it intriguing and wanted to figure out the heat transfer behind it, so our project was to try and replicate this phenomena and explain why it happened. We hypothesized that this was occurring due to a large temperature distribution from the oil to the glass. So as the hot metal would go into the oil, it would heat up the outer edge of the glass hotter than the inside of the glass, and that would cause thermal expansion and would cause the glass to crack. To analyze this experiment, a surface energy balance was used. The surface energy balance says that the convection from the oil should equal the conduction through the glass. The reason water is not a part of the energy balance is because water is treated as an insulator in this experiment. For the conduction through the glass, Fourier's law was used. Fourier's law states that the heat transfer due to conduction equals the thermal conductivity of the material times the temperature distance over the thickness. It was found through another experiment that in order to crack glass for a 4 to 6 millimeter thickness, there needed to be a temperature difference of about 125 to 146 degrees Celsius. The temperature gradient is important because through it, thermal expansion occurs, causing the crack to propagate.
The materials necessary for this experiment include a metal bowl, a propane torch, a thermocouple, pliers, water, sunflower oil, a glass cup, and a piece of metal. Sunflower oil was selected because the YouTuber who performed this experiment suggested it, and a glass cup was used instead of a glass jar because it was the thinnest piece of glass we could find, and as described in theory, the thinner the glass, the lower the temperature difference that is required to create the same temperature gradient that would crack the glass. The procedure for this experiment was to place the glass cup in a bowl and fill the glass with water. We then filled the bowl with water while keeping it below the water level of the water inside the cup so that the water inside the cup could act as an insulator and keep the inside of the cup at a constant temperature. We then poured a thin layer of oil outside the cup to be on the surface of the water, heated up a piece of metal to above 350 degrees Celsius with a torch, and then placed the metal into the layer of oil, being careful not to dip it into the water underneath the oil, as that would cause the water to boil and oil would spatter. The first time we performed this experiment, we tried to follow the video as closely as possible. We set everything up as described in the prior slide, and we took a razor blade, heated it up, and stuck it in the oil. However, the glass didn't crack, and while the razor blade was in the oil, we were measuring the temperature of the oil, and it didn't get higher than about 36 degrees Celsius. And so, yes, it changed from 22 degrees Celsius to 36 degrees Celsius, but it didn't heat up very much at all because we were expecting or wanting 100, 200 degrees Celsius. And so we decided to try again. The second time we decided we should use a piece of metal that is more massive because while the piece we used, pictured here, the right piece of metal in the picture, while it doesn't have a lot of surface area that we could stick inside the oil as the layer of oil was thin, it has more mass and therefore could hold more thermal energy. And while the surface area of the razor blade allowed it to transfer thermal energy faster, the mass of the razor blade made it so you couldn't store as much thermal energy in it. So while this may be slower, our hope was that it would build enough thermal energy into it and raise the temperature of the oil enough to crack the glass. While we were measuring the temperatures, the temperature of the glass itself raised to 146 degrees Celsius. So that increased a lot from the first attempt. So we were able to store a lot more thermal energy in the oil and then the glass. However, it still didn't crack the glass. So we decided, okay, we got the outside of the glass really hot. So let's try and make sure that we keep the inside of the glass really cold because we need this temperature gradient. So the third attempt, filled the cup with ice water instead of just room temperature water, and tried it again. Set everything up, heated up the metal rod, and still the glass didn't crack. Okay, so we were trying to figure out what to do next, and so we thought we'd try the most extreme option we could think of. Our final attempt to get this experiment to work was to fill the glass with dry ice instead of water or ice water. Dry ice has a temperature of negative 78.5 degrees Celsius, which is much colder than what we'd had in there previously. This would enable us to create a much greater temperature gradient, which should cause the glass to crack. We chopped up the dry ice and made it really fine so that we could fill in all the cracks and really fill up the glass cup and get contact everywhere, so the inside of the glass really was negative 78 degrees Celsius. We couldn't measure the inside of the glass with the thermocouples we had, as the thermocouples were not rated to measure that low of temperatures. The outside of the glass, after performing the same experiment, was measured to be 156 degrees Celsius, which, when we look at the gradient, we get, or the difference between the inside and outside of the glass, we get more than 225 degrees difference, which should be more than enough to crack the glass. This YouTuber tends to post reliable videos that actually work, so we are hesitant to say that his video is fake. However, under his conditions and even trying to make the experiments more extreme with each iteration, we could not get the glass to break. We believe that the temperature gradient of the glass is what should cut it, and we created a greater gradient than he could have with our addition of dry ice into the glass cup. So we believe that there must be some other phenomena going on that we are unaware of that is enabling the glass to break.